Good day, ladies and gentlemen. This is the 16th lecture of the series of lectures about the RM software for filter design. We will speak now about the synthesis of digital infinite impulse response filters produced from the analog prototypes by bilinear transformation. Here is the content. After the introduction, we will give a short comparison, short parallel between finite impulse responsive and infinite impulse responsive filters. Then we will go for transfer function decomposition. We will introduce the bilinear transform. We'll look to the architecture of the digital filter, and finally we will go for an example. Digital signal processing means dealing with discretized signal expressed in numbers in a form convenient for electronic implementation of the mathematical operations. Digital filtering is its important part. Two types of digital filters are in use, the so-called non-recursive or finite impulse responsive filters and recursive or infinite impulse responsive filters. Since the subject of digital filters is very broad, in this chapter, or by the RM software, only one of the two types was chosen, and the rationale of the selection was explained in the next discussion. Parallel architecture is recommended, as in most of the previous chapters for analog filters. Here, there are special reasons related to the stability of the solution. Finally, bilinear transformation of the corresponding analog counterparts was used. In this following set of tables, we will parallel, we will contrast the infinite and finite impulse responsive filters using different criteria. First criteria is the phase, linear phase. IIR filters are denoted here by D, which says disadvantage, since controlling the phase is a difficult task, while FIR filters, FIR filters, may be created so that the phase is always linear. Of course, there is a price for that. Stability is jeopardized in IIR filters, and one has to use parallel synthesis to mitigate the stability problems, while the FIR filters are always stable. There are no limit cycles, no oscillations. Sensitivity is more exposed in IIR filters, and to mitigate, parallel synthesis is also recommended, and it is less exposed with FIR filters or by non-recursive filter. Now we are speaking about the order of the filter. The order of the recursive filters to reach the same selectivity is incomparably smaller than the order of the non-recursive filter, which means much more hardware will be used if hardware solution is taken, or much more memory if software solution is used. It's not too forget that complexity leads to a latency due to the time needed to process the signal. Control of the stop band attenuation value is of importance for filtering at all, and when we speak about recursive, the stop band attenuation may be controlled easily, which is not the case in non-recursive filters, and that is a problem because we never know what will happen. Then power consumption is, of course, for simpler filters, recursive is smaller. Latency, as we mentioned, is much smaller in recursive filter than in non-recursive. Then we will speak about specific properties. The recursive filter, when the recursive filters are considered, the order of the filter affects both the minimum stop band attenuation and the transition region. There is a design freedom to control the stop band attenuation, and one may use the transmission zeros to position and the order of filter simultaneously. On the other side, the non-recursive filters allow for polyphase implementation, can always be made casual, but the minimum stop band attenuation is not affected by the filter order, which is a specific, very property. So you are not in a position to control this value. So we will go for the recursive filters because we have analog prototypes and we can obtain recursive filter transfer function by bilinear transformation. It goes in this way. First, we have to decompose the transfer function into partial fractions. As we mentioned, parallel realization is sought since it provides for stability. This is the bilinear transform, and below is how the transformation is applied. Now the fractions are transformed from the S into the Z domain. The first row is the original S domain. The bottom row is the transformed Z domain. And here are the cells realizing the second order and the first order cell, while the whole filter is a parallel connection of these cells. If the order of the filter is even, then there are only second order cells in parallel, and if it is odd, to the set of second order cells is one first order cell is added in parallel. So that's all. To exemplify, we will use a 14th order Legendre band stop filter, which will be extended with 6 transmission zeros at the positive omega axis. The maximum passband attenuation will be 3 dB, and the minimum stop band attenuation will be 40 dB. The central frequency of the stop band will be 100 kHz, and the cutoff frequencies are the upper, the cutoff frequency of the upper passband is 125 kHz, and the cutoff frequency of the bottom passband is 75 kHz. we will use a sampling frequency for the bilinear transform of 10 megahertz. Here are the poles of the S-domain solution, a bandpass filter, obtained through a series of steps in the RM software. For the Halpern filter is produced, then transmission zeros are added, and then transformation is done to get a bandpass solution, which is here presented. On the right hand side is the top half of the complex frequency plane to show the location of the poles and zeros. Poles are blue and zeros are square. Zeros are, of course, on the omega axis. One may notice that there are 7 zeros, but the seventh, the one in the middle, is in fact the infinity mapped at the central frequency of the stop band. Now, bilinear transformation is performed. On the left-hand side are now the zeros and the poles of the digital filter. We are still now speaking with normalized values, as you can see, and on the right hand side both halves, and you can see that the red squares, the zeros, are on a unit circle which is encompassing the whole space where the poles or zeros may be located for our stable response. Here is what is now a real filter. Here, after the transformation and after performing the whole activities related to bilinear transform, including pre-warping, we are getting now the coefficients of the transfer functions of the second order cells, and here are 7 second order cells. But since we are speaking about a band stop filter, there is one cell which is connecting directly, the first row here, directly the input and the summing. So in fact, it's going directly from the input to the output, and you can see its transfer function is of the first order. Of the first order. You see beta is 1, that is the last, and delta is 1, right? It is 1/1. There is not first order, but 0th order. Okay, these are the cells, and with these numbers, cells are created one after the other. And finally, we may have the response. Here is the response of, in fact, the gain of the band stop or notch filter, and you may notice the slight asymmetry. On the right hand side of the picture, it is broader than it planned, and attenuation, which is also distorted. And looking to these two figures, we have a better view of the passband and of the stop band, depending on where we are looking. Okay, that would be a short story about how the RM software for filter design is creating digital filters. One should mention that the final result here are numbers, coefficients of the cells, which are given with different accuracies, which means 8, 16, and 32-bit accuracy, which is depending on the implementation by the user. User may choose among the solutions which are offered in the report. Okay, that would be all for this lecture. Thank you. Thank you very much for your attention.